Let's begin again with the MRSA percent resistant data in the wide format. That is, with the columns having each year's worth of information. It might be of interest to understand if the percent resistant within each state is related from year to year. So we already know that they might be, considering that it's within the same state and those states make up the same hospitals and likely make up the same labs. So there might be a relationship from year to year. And that's actually one of the reasons that we created a different score to alleviate the dependence between the two different years. In this case, we actually want to investigate how related each of these years is to one another. So let's begin with 2011 and 2012. This is the preliminary investigation you should do for an analysis with two continuous variables like we have here. So I'm going to take both 2011 and 2012 and do a distribution on them. What we're looking for here is any outliers, any strange observations, anything that we need to be concerned about. We're also looking to understand the mean or center of each variable, as well as the ranges and the medians, so that we're familiar with each variable on its own, such that when we get it into a y by x graph where we are displaying both variables simultaneously, that we have a better understanding if something looks out of the ordinary or from what was expected. We can also see here that we have 42 observations in 2011 and 44 observations in 2012. That means at most we will have 42 observations in our plot that shows them together. And in fact, it may be less. What we have to have is called complete data. So that if the two that are missing from 2011 to 2012 are the same that are missing, then we should have 42 observations. However, there could be some in 2012 that have data in 2011, some in 12 that don't have it in 11, and some in 11 that don't have it in 12. So we may see an N larger or an N smaller than 42. We'll have to determine that when we fit them bivariately. It doesn't look like we have any outlying observations. There's one low percentage notice here on the outlier box plot. You could investigate that row to make sure that's a valid response, that the 16.7 here is a real value. But otherwise, the variables look relatively as we would expect. We can also do an assessment of normality for both of these variables. And as we know about the test scores, we've seen them look to be relatively normally distributed before. Univariate normality, that is normality within each variable in one variable, the uni and UNI part of univariate, is not required when we're looking at bivariate normality, but it's helpful. So both of these variables appear to be relatively normally distributed. So when we look at them in a fit y by x situation, we should have fewer concerns about the bivariate normality. Okay, so knowing what we know about 2011 and 2012, let's go ahead now and go to the Analyze Fit Y by X platform. And we're going to put our 2011 as our X and our 2012 as our Y, and press OK. And we get this general plot from JUMP. And let's walk through this plot. It shows us 1 point, row 18, you can see here, with a value in 2011 of 52 and a value in 2012 of 23.5. You can roll over this point here and it will take us to row 45. Anytime you click on a point, it will highlight that data. So you can see here one row selected, and then you can click outside in the white space and that will unhighlight your individual point. In addition, you could look at collections of points, clicking on and pulling or clicking and rotating your mouse, or on a trackpad, you can simply click and then create the square, and that will highlight all of the points in that section of the graph. A couple of other things that we want to talk about here is that we want to have on variables like 2011 and 2012 where we're testing the same thing. We would like to have the same axes for those. So because the axis is wider from 10 to 80 in 2012, we'll change the axis here in 2011. To do that, you right click or control click on a Mac for the axis settings, and we'll change this from 10 to 80, and we'll press OK. And now you can see that they're on the same scale. In addition, we would like to have the same aspect ratio. That is, we'd like the length of the x-axis to be the same as the length of the y-axis. To do that, we'll right-click again to size scale, frame size, and here we'll say let's make them 450 by 450. And you can see it will slightly adjust here to be a square frame. This allows for a better perspective in terms of the relationship of what would be a perfect relationship, which would go diagonal to diagonal. That is, every value in 2011 has an identical value in 2012. So now we know that a perfect relationship would go from the bottom corner to the top corner. And we can sort of see how our relationship compares. In addition, we can think about what the mean value in 2012 would be. And you could click there and do the axis setting, and you could actually add a line at the mean value. To determine the mean value again, go back and do a distribution on 2012. So we'll put 2012 here. 2012, and our mean value of 2012 is a 47.57. So I'll go back here into my axis settings and I can put in 47.57, and I can add this line there and press OK. And you will now see that this is the mean value of 2012. That will help us assess whether or not we have a relationship between 2011 and 2012. If we did not have a relationship, we would expect to see an equal number of points above and below the axis, as well as randomly scattered about the distribution of x. That is, as our eye goes this way on x, if there was no relationship, we would expect to see equal numbers of points above and below the axis at every point in x. In addition, we can assess for equal variance. That is the spread of the points as we go across x equal across the top and bottom? And so we sort of see that here. If you look in this area right here, as we move across x, we see the spread of points, the distance of each dot from the x, the 2012 mean line, seems to be about equidistant above and below. We can see that there's a point down here, but there's also a point up here. Those are about equal distance from this mean line. And that is how we begin to assess our assumptions for correlation. One of them is linearity. Can we envision a line fitting this data? Is there any curvature to it? Can we assess for equal variance? Does it look like we have equal number or equal distance of points above and below the line as we go this way on x? And then we can assess the potential relationship. Does it look like knowing values of your x variable help you determine values of your y variable? In addition to that, we need to learn how to assess normality. That is here under the red drop-down. Ask for the density ellipse, 95%. What you want to see with normal data is that 95% of your points will be within this ellipse. If you have more data points outside, so we seem to only have 2 data points outside, so 2 out of our 41 variables here that have both an x and a y. 2 out of 41 is less than 5%, and so we can be somewhat confident that we have normally distributed data here. So this is how you investigate your data for fit y by x. It's also how you prepare it for a presentation to make sure that you have equidistant x and y axes. Let me quickly remove this fit here and walk through some of the things that can happen. So I'm extending this out. You can see how the impression of the relationship has changed now that I've made the x-axis much longer. You could also see if I then made the y-axis much shorter, the impression of the relationship of your data would change. Or let's say that I made the 2012 data go from 0 to 100. And I could put this back at its original settings of 20 to 70. And now you can really see that your interpretation of the relationship between 2011 and 2012 is different than if you put the correct perspective. So equal length axes, that's called aspect ratio. So again, we can do that under size scale, and I can change that again to make them match. And then also, if your variables are on the same scale, like ours are here, you want your axes, the scaling of your axes to match, and we can put them back at 0 to 100 for both of them. And now you can see that we'll get a clearer image of the relationship between our two variables. So things to pay attention to: the scatter of the data about the mean line, the scatter of the data above and below the mean line as you move across the x variable, the normality, look at that with the bivariate density ellipse. We want to look at whether or not a linear fit is possible. Can we fit a line to this data, or is there curvature? And in addition to that, we want to pay attention to the aspect ratio and then the scaling of your axes to give the most accurate or unbiased picture of your data. In the next several videos, we'll determine how to actually get a correlation. We'll determine how to get a slope or fit a line to the data. And we'll determine what to do if our assumptions of linearity and normality are not met.